Well, I think the rest. Well, okay. So here's the layout for the rest of the class. There's 2 lectures right after Thanksgiving on transactional memory, and those are real kind of heavyweight lectures. There will be exam problems on them, or almost certainly be exam problems on them. The other 3 lectures that we have before now at the end of the quarter is today's lecture on domain-specific programming systems, and then the last week, Kunle's talking more about specialized hardware, not as programmable processors and the energy efficiency of them. These other 3 lectures are a little bit more like we want you to know about them and be aware of them as you proceed further, but exam questions would be more conceptual and not like, work this out or something like that. So here's so I'll just get started, and the systems we'll describe today are actually pretty cool. So the goal of what I'm trying to do today is 2 things. One is, so far in this class, you have implemented code in what I consider to be fairly low-level programming systems. Essentially C, C++, CUDA is basically that, ISPC is basically that. And more or less, you've done everything. Like the one thing that you got that was really convenient was both ISPC and CUDA basically took over the responsibility for generating SIMD instructions for you. At the very least, you didn't have to worry about that. But most of the rest of the major decisions were made by you, and that was intentional. You now know how a thread pool might be implemented, so when you call ISPC tasks, you know exactly what they're doing, and so on and so on. So now we're going to say, okay, you kind of know how you would implement, things from scratch. What are the higher level abstractions that would be good to present people that might be experts in a domain, but not the folks that have taken 149 or really are interested in implementing things? So I'm going to talk about that today, and largely I'm going to talk about it through the context of 2 case studies, 2 examples. Both of these actually have some Stanford relation. We're going to talk about the programming language that's used to author all of the image processing, the photo app in Google Android phones. So it's and every image that's, or at least to my knowledge, at least a couple years ago, every image that went through Instagram was going through filters and processing from a language called Halide. And then there's this research language developed at Stanford called Lisp, which is, it was a research language, to be honest, you'd probably never ever encounter it, but it's actually got some great examples of the value of high-level abstractions in it. Okay? So that's what we're going to talk about. So the premise here is that, we haven't used all of these programming systems. Some of them might be familiar to you, but if I am if I'm trying to develop a high-performance application, I need some pretty smart people to be able to optimize it. I need CS149 students, and in the grand scheme of programmers, CS149 students are pretty few and far between, right? And if you look at the range of performance that even CS149 students produce on their assignments, really code optimizers are even fewer and far between. So proof by assignments 1, 2, and 3, and probably even proof by assignment 4 for sure. And throughout computer science, whether you're a systems person, whether you're a programming languages person or compilers person, there's kind of always been this sort of holy grail, or this unicorn of characteristics of a programming language, right? Like, first of all, you'd like to be able to just productively express the program you want to write. And in fact, these days with LLMs, there's a lot of interest in that, saying I want a program that adds a bunch of numbers and it spits out the Python code. So you'd like to be able to go from an idea to a working correct program very quickly. You want to be productive. And many of you use Python as probably your most frequent language because it's a pretty productive programming language. And then, in many cases, you probably like a high-performance programming language because these days, machine learning, data science, big graph algorithms on terabyte-sized graphs, et cetera, or image processing on 10 megapixel images, you're going to want performance because it's got to run on an iPhone, it's got to run on a data center. And then last, historically, people have said, well, programming language should be general. You should be able to write whatever program you want. And there were these kind of 3 axes of rating a programming language. And like, what is the programming language that nails all of these, that scores really high on these fronts? And if you look at many widely used programming languages, and really this has been changing over the last 5 to 10 years. But if you look at a lot of the long-term ones, they kind of go on some axis, right? Like if you're a web developer, you might write a lot of code in JavaScript. You can write whatever you want in JavaScript, but you can hack some stuff up pretty quick, but it does, and you can hack basically whatever you want, but it's not going to be that fast. Or if you're writing here in C++ or Rust, and I'll even put Java and CUDA in this category, these are all different levels of performance, to be honest, but you can write whatever you want again, and you'd choose to use C or C++. So, that would be your thing. Like, this needs to be fast, I'm going to write it in C, or it needs to be GPU accelerated, I'm going to write it in CUDA. And so a lot of the more successful languages were kind of on these axes. And so what I want to talk about today is this empty line here between productivity and performance. So we're interested in, I put Ruby down there as well, in domain-specific languages where we say, we care a lot about being productive. Like, for example, PyTorch. I want to be able to hack up a new neural network very quickly. I want it to be extremely efficient, not just like parallel efficient, but if we're talking about PyTorch, we're like, we want to use GPUs or we want to use accelerated TPUs or something like that. But I'm willing to give up the fact that I can kind of express anything I ever want, right? And so some of the examples here, you probably have encountered a bunch of them, right? Like, PyTorch is not the language that you would use to build anything you want. It's a language that you use to express your tensor operations, right? SQL, very constrained language, but it's a great language for querying a database. And you don't think at all about how those queries are executed in parallel on a big database. You just hope Oracle or Postgres does the right thing. But you just say, I'm looking for, all records in my database where the first name is foobar or something like that. Even something like MATLAB, I would put in this example. Anything else come to mind as things that you commonly use that you might sort of categorize as being similar in spirit to some of these things on the left, this left edge? Yeah. G what?
GDOG. It's used for like.
I actually don't know what that is.
Geospatial.
Oh, for geospatial databases. Yeah. Okay. So that's another database query language, except it's centered around the notion of 2D space. Okay. Yeah. So any kind of database query language kind of fits in the thing. If you're in graphics, something like OpenGL, and we're used to writing in fairly domain-specific languages in graphics. These days, machine learning, all of it is done in fairly, and there's different levels, there's like PyTorch, and then there's a whole bunch of things built on top of the PyTorch to make your life even easier if you want less and less flexibility. So that's kind of the idea of today, is the thesis is, and these days, I think you're seeing the results of about 5 to 10 years of emphasis on domain-specific languages. And if we go back about 10 years, it was probably a little controversial to say, hey, like, we're going to give up on the flexibility of C, C++, Java, and we're going to force you all down a narrow path, right? So this is the big promise. And usually in this class, we actually give you this lecture after we've talked about specialized hardware. We haven't talked about specialized hardware yet. But just keep in mind, like that high performance is not just parallel, but it could be like using a TPU, it could be using an accelerator, it could be using any of the 5 different processors that are in my Apple Watch, things like that. Okay. All right. So, here are some examples. You pointed out a few to me already. I added a few more here. So the idea is to write a program quickly and write it once. And I'm going to write it using primitives that the compiler, the system knows about. And it knows enough about what I mean by various primitives, like, for example, PyTorch knows what an ND tensor is. For example, SQL knows when you say select this row, like it knows a lot about what selection means. And it's going to leverage that knowledge to give you the best possible implementation on whatever system you're running on. So if I say select everything from this database, like how is the data laid out? What is the algorithm, the index structure used to, is it a binary tree? Is it a B tree? Think of all these decisions that go into implementing that database. As the programmer, I just say, please give me a relation, give me a table that has all of the results of this filter. And on different systems, that implementation can be very, very different. In PyTorch, you're going to say something like, please take this tensor and pass it through this conv layer. And if you're running on a GPU, that's going to be some cuDNN implementation. If you're running on Intel, it might be a completely different implementation. If you're running on a Google TPU, it could be a completely different implementation. So let's just kind of go through some examples to think about some of the decisions that folks make when designing these domain-specific sets of abstractions. And the first example that I'm going to give is a little bit from like sort of my neck of the woods in graphics and image processing. And it's a language called Halide, which is the language that's used in practice to implement the camera application on Google's Android phone. So if you have an Android phone and you take pictures, you are running Halide code. I'm not up to date, but as of like 4 or 5 years ago, if you uploaded a picture to Instagram and it went through an image processing filter, many of those were running in Halide code at Meta. So this is actually, it's not a widely used language, but it's a language that's used by a bunch of people that care a lot about performance. Okay? And it had origins at Stanford, even though it was mainly developed at MIT and then later at Google. So before we start talking about what are the primitives Halide gives you, we actually have to talk about what is the workload that people in this domain are trying to write. So here's an example, and I'm curious, in 30 seconds or less, can you tell me what this code does? Any sense? And it blurs an image, which you can tell from the function name, yes. But how does it blur the image? Like, what's the filter size? How is it parallelized? How is it vectorized? It's pretty gnarly, pretty gnarly. And this is like, if we were in the assignment 1 time frame, and we replace load 128, which is your MMX intrinsic, so we change that with like CS149 intrin, you would have done this yourself. You would have done this yourself. Now let me ask you a different question. What does this code do? This is C. This is regular C. I didn't give you the function name this time, so you can't cheat. This is a convolution. This is a 2D convolution. I give you an image, a 2D array, a matrix of pixels. In this case, it's a monochrome image because there's not red, green, and blue. It's just a single intensity per pixel. And every output pixel at the same location is the average of all the surrounding neighboring pixels. So this is the for every output pixel loops. And then for every output pixel, please loop over the 3x3 block of neighboring pixels and average them together. Add them all up and then divide by, or multiply by weights. And weights is 1/9 everywhere. Okay? And back in the DNN lecture, I told you if you ran this C++ code, you would blur an image and it would look a little bit like this. All right. So here's that code. And so here's my question to you. Let's analyze it a little bit. What is the amount of work done per pixel? How many arithmetic ops? Let's do this again. How many arithmetic ops per pixel? In other words, look here. Shout out. Floating point arithmetic ops. There's basically one multiply here and an add. So I'm doing 9 multiply adds and then a store, right? So the cost to do this is 9 times width by height. or if we decided to think about the filter being an n by n filter and not a 3 by 3 filter, it would be n squared width by height. That's the amount of work we do. So that's the total number of ops. Now I need to give you just a small piece of information if you knew this about graphics. If you look at this filter, you can actually separate this filter, which is a 2D convolution. You can separate it into two 1D convolutions in this case. So I'm going to write it a little bit differently just to be optimal before we start parallelizing it. So I can get the same result by actually just blurring 1D convolution across all the rows. So every pixel is the average of the three, the left and right neighbor and itself. And then I take that result and I blur vertically. And if you think about it, after the horizontal blur, I've added up 3 numbers, and then after the vertical blur, I've taken those partial sums and added 3 of them together. So I'm doing the exact same math. Okay. So that code might look a little bit like this. So I wrote it in C here, and then on the right side, I'm showing you the allocations. So the input is size, width by height. The +2 is not that significant. I just didn't want to deal with boundary conditions in my output. Then I basically shrink it by 2 elements when I'm blurring horizontally, and then I shrink it by 2 elements when I'm blurring vertically. Okay. So what is the amount of work I do now? So it used to be n squared width times height. Now what is it? Now it's 2n width times height, which, dropping from 9 operations per pixel to 6 might not seem all that significant, but what if it was a 7 by 7 filter? Now that's 49 operations per pixel versus 14. We're starting to get like a factor of 3 or more in terms of math. And if you blur an image in Photoshop, you often might do something that's like a 100 by 100 blur radius filter, and so things can get gnarly pretty fast. Okay, so that's good. We've reduced the number of math operations we need to get this thing done. Do you see anything that may be not so good if we think about some of the other things we think about in this class? Yeah. Okay, so one thing that is unfortunate is that I basically increased my memory footprint by 33%. Right, so I used to need an input and output. Now I need an input and output and a temp buffer of the same size. And that actually could be not a significant thing if I'm dealing with like a 12 megapixel image on my phone, right? Like I'm allocating another 12 megapixel buffer, 12 megapixels times red, green, blue. Often red, green, blue alpha is arguably 48 mega floats, or 48 megabytes. If it's so, like I just allocated 50 megabytes of memory, and on a phone that can matter. It can definitely matter. Anything else that you notice? So what are the things we often think about? We think about so parallelism. There's no parallelism here. We haven't talked about that yet. But we talk about work done. We talk about memory footprint. We talk about memory bandwidth and arithmetic intensity. We talk about SIMD coherence, but again, there's no parallelism here yet. Yeah.
Like the buffer again.
Yeah, so we, before, keep in mind that, let's look at this program. How many times does every input get read? Technically, every input gets read 9 times, but effectively, how many times will it get read from memory? Probably once. And you got to be a little bit careful about that, to be honest, because we talked about this blocking thing. So it means that if you can hold 2 rows in cache, then you'll be able to hold the data around long enough so that you're only going to read it from memory once, right? So as long as a couple rows can fit in cache, this thing is going to read every input element once and certainly write every output element exactly once, okay? And now think about this one. This one reads every input element once, writes every temp buffer once, then reads every temp buffer element again, and then writes the output once. So my arithmetic intensity, not only has my memory footprint increased, my arithmetic intensity has sort of decreased by a factor of about 2. So if we were bandwidth bound before, we are now even slower. If we were compute bound before, okay, maybe we made an improvement. Okay. So So we actually kind of already talked about this a little bit. I sort of pointed out all the places where data gets reused. Exactly. Okay. So, question for the audience: is there a way to do better? And let me seed the thinking just a little bit with an algorithm that looks a little bit like this. And I'd like you to try and make sure, just take a look at this. So this might be nice to talk over with someone. And I've given you some hints to help you understand this. What is this implementation doing? It does not allocate more than 3 rows of temp buffer. It takes a little bit of time to digest. So if you want to talk it with somebody, or if you just want to puzzle through it yourself, I'll give everybody about 30 to 45 seconds to kind of push through here. The key things are the things I've highlighted. Notice that the outermost loop is over rows, and then this loop is over 0 to 3. Okay. So what's going on here? How could we explain this? Like tell me, if you were trying to explain this to me in office hours in high level language, what's going on here? Yeah. Oh, sorry. No. Yeah. I thought you were volunteering. Never mind. Yeah.
I guess one way I would maybe think about it is you're doing the same algorithm as the last slide.
Yes.
But you're doing it a bunch of times on different chunks of the output.
Yeah. So what I'm doing is that. Look at this. So what I'm doing is I'm saying we don't need the whole temp buffer, the whole intermediate. What I'm doing is I'm doing the first pass, but I'm only producing 3 rows of output. So I'm taking 3 rows and blurring them horizontally. And that's all the information I need to then blur those vertically and get 1 row of final output. So in other words, you can think about it as you can read the code in the following way. The outermost J loop is for every row of output. Then first generate 3 temporary rows that are needed to produce that row of output. And then take those rows and compress them and blur them vertically in order to produce that row of output. So the way I like to think about this piece of code is I just think about the for loops and I say, oh, look, for every row of actual output, first produce the inputs that are needed, and then consume those inputs to produce the row of output, and then start over again. So the nice thing about what I did was my temp buffer allocation moved from the entire size of the image down to approximately about 3 rows. Which are good because those 3 rows probably can fit in cache now. And I got my arithmetic intensity back. So I'm doing this 2-phase algorithm, which I thought was good, without the extra allocation. And I made the temp buffer small enough that writes to that temp buffer and later reads will hit the cache. But is there, how did I get, what was the cost that I paid? Yeah.
Rows multiple times sometimes if they overlap, because you're doing 3 every time.
Yeah, so notice what's happening is every row of temp buffer really can be reused 3 times. But I'm producing a whole row of temp, 3 rows of temp, using it, then throwing out all that information, and then computing another 3 rows of temp over and over again. So I'm recomputing a bunch of things, which is diminishing the benefits of sort of this 2-phase approach. In fact, if I said how many operations per pixel do I compute, can you compute what it is? Or maybe how many operations per row? That might be an easy way to think about it. So for every row of output, what do I first do? I do 3 operations per pixel for 3 rows. And then I do another 3 operations here. So I do 3 times 3 plus 3. So I end up doing 12 math operations per pixel, which is actually worse than I started. So I've gone backwards. But it feels like I'm getting closer. So what are some ideas? So I want to minimize the math that I do. I'd like to get it down close to this 2n. But I want high arithmetic intensity and low footprint. What can I do? Yeah.
Instead of completely rebuilding the temp buffer for every row, just preserve the last two and then write the new.
Okay, so if we're thinking sequentially, one thing we could do is we could just think about that buffer as a rolling buffer. Slide 2 rows down and populate a new one, and then we're off to the races. Now we are going to pay the cost of sliding the 2 rows down, just a mem copy, cache, so that could get a little bit annoying. Or we could actually just have this code sort of use indirection to refer to the data. But now this code's going to get a little ugly. And in fact, by the way, if you do this, you will find that the extra math indexing you put into this code will slow you down more than other stuff on almost any modern computer. Any other thoughts? By the way, if you do this sequential, if you do this sort of sliding window, rolling buffer thing, you all of a sudden you just created dependencies between every row. And we didn't have dependencies between every row. So that could come back to bite us when we want to parallelize this thing. Could. Any other ideas? Yeah.
Split up the buffer into 3 and then just keep them as 3 separate pieces.
Okay, so by splitting up the buffer into 3, are you suggesting that let me cut the input into horizontal, like 3 columns? I'm not, okay, so let me make sure I understand. So the temp buffer is currently 3 rows, and you're proposing to cut it horizontally into 3 columns as well, 3 chunks?
I'm proposing temp buffers right now width times 3, so you just make a temp buffer of 3 of width. So it's a 2D array with 3 and then width.
But that's the same thing exactly in memory.
Alright.
Yeah, that's exactly the same. You just are using the convenience of 2D indexing in C, and I'm just flattening it myself. But under the hood, the compiler would flatten it exactly. So I think we're saying the exact same thing.
But if you keep it as temp buffer 1, 2, and then 3, actually separate variables, would they still be this the same?
No, they would be contiguous allocations, but maybe not contiguous in the heap, each of those. But I don't think that solves my problem. My problem is that either I have to copy contents from those buffers to each other, or I have to index into the appropriate buffers here. So we're still in the same place. You actually just spread out the data even more a little bit. Yeah. Any other ideas?
I don't know if it's similar, but kind of just blocking into maybe squares or something, and you will have some overlap on the edges where you pre-compute, but you could then have smaller buffers.
Okay, and that's actually, there's a couple of ways we can go, and I like that idea. So first of all, think about how I've set up the problem here in kind of a row-wise thinking. The way I would say is for every row of output, independently, compute the 3 rows of temp that you need, and then process that row of output. And then do that for all rows of output. What you're saying is the problem with my solution is that for every row of output, we kind of compute an extra row above and below. And so for everything I do, I have 2 rows of overhead. Well, what if instead of just thinking about every row of output, we said for every 10 rows of output, compute 12 rows of intermediate, and then bang through it. We're still computing some extra stuff. But now it's only 2 extra things for every 10 instead of 2 extra things for every 1. Right? And that's where I'm going to go next in the next slide. So here's, all I did here is now look at the temp buffer. The temp buffer is chunk size plus 2 times width. So mentally in my head, I'm saying for every chunk size rows of output, first produce chunk size plus 2 rows of temp, and then produce your output. And what's the overhead now? It's getting, as chunk size gets bigger and bigger, this is going to trend towards my original 2n algorithm. Okay, so I'm encouraged to make chunk size as big as possible. But what happens if I make chunk size too big? Chunk won't fit in the cache, and I get no benefits of the chunking at all. Right? This is the exact same, similar to this blocking idea. So this is a way for me to change the program. And let's say if the chunk size is 16, if the chunk size is 16, we're roughly, if you actually work through the non-even math, it's about 6.4 operations per pixel. So a little bit more than 2n, but certainly not 9, and certainly not n squared for larger chunk sizes. Cool. So this is like, that same producer-consumer fusion trick that you saw first in Spark. Then we saw it in the matrix multiplication lecture. And now you're seeing it again, reordering the computation to maximize arithmetic intensity. But here we're actually saying we're willing to recompute a little bit in order to maximize arithmetic intensity. So that's not something that's appeared in the other things. Okay. Now we're still not done, right? Because we haven't talked at all about SIMD. We haven't talked at all about parallelization. And a bunch of other small-scale things. How would you parallelize this computation, by the way? First of all, what can be parallelized and how I've set it up? Can every output chunk be parallel? Yes. And if you needed more parallelization, you could actually break the output chunks horizontally as well into chunks. And then I just need, I don't need 3 rows. I need chunk size rows, but not the whole width of the row, just like the width of the chunk plus 2. Now there's another way to go about this that suggests the sequential thing. I could have not done this at all. I could have gone back to this algorithm where there's only a single temp buffer of a few rows, and I could have taken your idea of we're just going to sliding window the thing, and then I'll get my parallelism by chunking the output into columns. So I'm just going to slide down every column, hope that I have enough parallelism across my chunks, and that's another way to do it. So there's a couple of different ways you could do it. Okay. Yeah. So essentially, if you look carefully at this code, what it's doing is exactly what we came up with. It's saying for every chunk of the output, and every chunk of the output is actually 256 by 32. For every chunk of the output, first compute a chunk of temp that is 2 elements wider and 2 elements higher. That's what these 2 for loops are doing. So it's kind of saying produce the output in tiles. And if you look at the outermost loops, it's for every tile in Y and X. First compute something that's 256 plus 2 by 32 plus 2, 32 plus 1, and 32 minus 1. Produce that using SIMD instructions. This chunk size fits in cache. And then take that chunk and produce the output. Would have been hard to see. But pretty easy to actually explain in English. Okay. So that's where we get into the domain-specific language. And by the way, every single time you wanted to try something a little bit different, maybe you said, oh, I want to go with like this option. And then you say, oh, I want to try that sliding window thing. Imagine how long it would take you to get to a sliding window implementation from this. If you're a good, really proficient, it might take you a full day or something just to try this thing out. Okay. So Halide is a language that's not really designed it's not like PyTorch that's meant to allow people that don't know much about parallel programming to get good performance. It's a language designed to allow 149 students to finish their assignments much more quickly. Right? So it's a language that for people that basically are like, oh, I know I want to try and block it in this way and go vector across this loop, but I don't want to write the code. So if ISBC says, I don't want to write this code, that's what it helps you with. Halide for image processing says, I don't even want to deal with all these loops and things like that. So I'll give you some examples of some Halide code. And halide is completely functional. So notice that there's no loops in this code at all. And halide has a concept of what they call a function, because this is functional. But you could think about these things as tensors if you wanted to. So let me look at the code for you. So blur x is a function that's parameterized on x and y. So in other words, saying blur x is a function that if you give me an x and a y value, the function will give you the value of the pixel at that x and y. That's what a function does, right? And the function is defined in terms of inputs and outputs of other functions. So this says that the output of the blur x function at xy is 1/3 times the value of the in function at x minus 1y plus, or 1/3 times quantity these three values, or in other words, the average of those three values. And there's another function, blur y, and its value at xy is the average of these blur x values. So I'm building up the expression tree to say, if you want to know the value at blur xy, this is the expression defined in terms of predecessor functions on how you get it. And notice that in is technically a buffer, which basically is a special function that was loaded from the actual input data itself. Yes?
I'm curious how you handle edge cases here, because if you put x and y as zeros, you're going to get n minus 1 or 0.
That's correct. So that's a great question. I'd like to not really deal with it. You should just say you should look up at n negative 1, exactly as you wrote the program. So the real question you're asking is, what is n negative 1? Is that an error? Like if it was an array, it's an error. You can, but since this is a domain-specific language, and domain-specific languages are meant to be productive, something I'm not showing on the slide is I could easily set blur y.boundary condition equals 0, or something like that. And halide compiler will emit the math that detects the boundary conditions and outputs the right value. So that's why I don't want to deal with it for the rest of the lecture. But that is a productivity benefit of the language of handling boundary conditions efficiently for you. And really what halide will do is it potentially will generate code, not where there's an if statement in the inner loop, but it will actually generate a loop for I equals 1 to n minus 1 that has no if statements, and then generate other loops for the boundary conditions and stuff like that, which would be absolutely messy if I showed it to you in this, right? So that's the productivity part of this. And I just want to give you some more examples. So this says that if I have a function blur y, which is defined on x and y and has some value at x and y, then here's a function called bright of xy, which is defined as the value of blur y times 1.25, value clamped to 255. So bright xy is just blur y times all pixels times 1.25, but make sure you clamp them to 255. And then there's even a gather. We talked about data parallel gather. Output at xy could be use the value of bright xy as an index to look up the pixel location in this function. So this is a gather. All of these other ones are maps over all x's and y's. So it's a functional programming language. And so we're defining the expression for how to compute xy. And then this last line of code just says, give me an actual C-style buffer where the values are, I have evaluated the function out at all values between 0 and 124 in x and 0 and 124 in y. Okay, so it's delayed evaluation, basically. And so the nice thing about this is we have these functions, and if you think about image processing, if I explain to you what is a blur, I don't give you a convolution. I typically say, the way you compute a blur is you take every pixel and you average everything around it. And that's exactly what this code looks like, right? So the expression is productive in that it handles boundary conditions, but the code looks like the math and the way we talk about the algorithms. So in some sense, the code looks a lot like NumPy or something like that. But just keep in mind that these are functions. These are not arrays or tensors. You can think about them as such, but I'd be careful, but don't. Okay, So if I wanted to think about this program as a DAG, a list of tasks, I would think about it as every one of these functions is a node, and they depend on prior functions. So I would say that in this case, look, so we have an input function. Blur x is derived from in. Blur y is derived from blur x. Bright is derived from blur y. And out is derived from lookup and blur and bright. So let's check that. Yep. So I have a chain of just dependencies, and output came from values in bright and values in lookup. Question? No? Oh, it might have been an iPhone. Okay, so first of all, does everybody kind of at least cursory understand what this program should compute? And I'm being specific about what it should compute, not how it should compute it, but what it should compute. If I populated in with a bunch of pixels and I populated lookup with a bunch of pixels, like loaded an image into it, you would say, yeah, I have an idea of what out xy should be. And this graph kind of gives it to you. Okay. So here is the halide representation of the two-pass blur that we've been talking about. We have an input, which came from an image. We have our first function, blur x, which says blur x at xy. Well, every pixel should just come from the average of these 3 pixels in. And then I have out xy, which comes from the average of these 3 vertically oriented pixels in blur x. So my entire C code, which, if we go back, this algorithm in C looked like this. In halide, it looks like that. So it kind of just follows the mathematical formulation of it. So that's pretty cool. First of all, it's a little bit more elegant. Like you can kind of read the code. If you were an algorithm developer, you probably know what this meant. Now, this code in it has two functions. It has 2 stages. That's like the dependency graph on the right. If you take a look at more realistic image processing programs, they have a lot of stages. And at least about 6 or 7 years ago, your Google HDR Plus, your camera application, that application was about 2,000 halide stages. So when you think about what this halide program means, if you were the halide compiler, you might in your head right now be thinking, okay, if I'm the halide compiler, and this was my program at the top, what I showed you on the last slide, I'm mentally translating that program to this implementation in a C-like language. For every function, allocate an array. Just turn a function into a tensor, a 2D array or a matrix. And then for every equality statement, for every expression, that is an operation that runs for every pixel in the output array and computes values. Right? So, in some sense, can you confirm that this makes sense? Like this is a valid implementation of that code up above. So the halide compiler basically just writes these loops for you. It's coming. So first of all, just like this is now precise. This compilation has generated a sequential C program, like assume these are for loops, that allocates these 3 buffers. Exactly what we said. I wrote this in C earlier in the lecture. So I first am establishing that this is a valid compilation of that program. And there might be additional valid compilations. Okay. All right. So a key aspect of any of these DSL systems is thinking about who your users are and thinking about what is hard for them, what do you want to make easier. So I would say that even though what I just showed you on this slide, it's kind of nice that I can write things in 2 lines of code. You could have written the C code in 10 minutes, right? So if I write 2 lines of code versus I write the C code in 5 to 8 minutes, that's not that big of a benefit, right? There's some nice syntactic sugar and stuff like that, but it's not that big of a benefit. Maybe if we get boundary conditions in there, it might help you a little bit and stuff, but that's not the real thing. The hard thing is if I go back, how long it would take you to come up with this, right? Even if you knew what you were doing in 149, you don't know what the right answer is for a particular machine. Like think about all the iteration you do on your programming assignments. So what halide is, the halide programmers had written a bunch of these things in assembly, right? And they say what we want is we don't, like it'd be nice to have a nice compact syntax. But what we really want is to explore the optimization choices that we know are likely optimization choices, and we want to do it very quickly. Okay. So the job is not expressing the image processing calculation. The task at hand, the challenge at hand, is to do your 149 assignment, which is to make it fast. And halide introduces a set of ideas that allow you to describe how you want to make it fast at the level that we kind of talk about it in lecture. Okay, so what halide has is if the stuff that's in the white background is the halide program that expresses what to compute, like expresses the algorithm, that is complemented by another set of programming primitives, which I'm not going to explain just yet, which is called the schedule. And the schedule is the explicit direction on how to generate code for this. Okay, and I'm going to read this off to you, quickly in English, and then I'll break it down over the next couple of slides. Here, the programmer has specified exactly the solution that we came up with, which is I want you to compute output in tiles of 256 by 32. Please go ahead and call the loops of those tiles x and y, and then x inner and y inner. So x and y are the tile or which tile we are, and xi and yi are the inner loops within those tiles. And then I want you to vectorize the loop that's called xi with 8-wide SIMD, and I want you to go thread parallel across the y loop. The result of that will be the code that I gave you on the previous slide. And if you're like, I don't know if this is working, maybe I should change my tile size, you just change the parameters here, and you get a new tile size, and it revectorizes it for you. Or if you say, I don't want to vectorize the xi loop, let's actually go ahead and do our SIMD over the outermost loop or something like that. You just change those parameters. So that's where we're going with this, right? Okay. So these scheduling directives give you a couple of different types of primitives. So some of the primitives are related to how do you iterate over the elements of a function. Row major, column major, blocked, and so on and so on. So these are just some different examples of iteration. Like, I want you to go serial over the y dimension. I want it to be x major and serial, so just what you'd think. Or I want it to be column major. Or I want it to be serial along all the y's, but along the x direction, you're going to be vectorized. Or I want it to be thread parallel along all the rows. All the different y's are different threads, but vectorized in this direction. So you have the ability to express all the different permutations that you think you might want. Okay, all right, so let's get into actually some details. So let's look at this one line of the schedule. And again, I don't care if you walk away knowing this, but these concrete examples give you a sense of what's possible. Is we said that, this out.tile basically says, I want you to compute the output not in row major order by default, but in tiles, and tiles of size 256 by 32. That's what that says. And we decided we were going to do that. And we might need to name the loops of the variables. So we're going to call it, the code says, if you need a handle in the future, we're going to create, in tiling the code, remember there's 4 loops. And we're going to refer to those loops as x, y, and then x inner and y inner. And then, so you can think about every one of these halide schedule statements as actually manipulating a loop nest that exists in the program. So by default, we had a loop nest which looked like this. By default, if that was the program, halide had this loop nest, which was for x, for all xy, create blur x, and then for all xy, create out. And so what that statement did said, hey, the loop nest that creates out? That's what our code did. It said, I want you to modify it so that it was a tiled loop nest, and I want you to call the 4 loop loops that would result from that tiling, xy and xi and yi. So halide is actually, there's a language for specifying your algorithm, and then there's a language that's imperative that describes a sequence of transformations on the loop nest that you want to create. So imagine that we did a transformation that created 4 loops here with an output that iterated over tiles of 256 by 32. Okay. Now, once you have that loop nest, so that out.tile like kind of returns the new loop nest, and then I say, oh, please vectorize, when you generate code for the xi loop, I want that to be vectorized. And when you generate code iterating over y's, I don't want it sequential, I want that parallelized over a thread pool. That's what that whole line says. And so the result of that would be some code for the blur x loop that used to be for all x and then all y. Now notice it has 4 loop variables, and the xi loop is vectorized, and this loop, just imagine it was parallelized with threads. So you're telling the compiler at a high level how you want to do this. Okay, so loop ordering is one class of things you do. And then the other class, what was the other big thing we did is we did fusion. And fusion is like putting some loops inside of others. So here I said out.tile, that created this output loop nest. And then remember, for every tile in my solution, I first had to compute the temp buffer that was needed to produce the outputs. That's this loop nest. So by default, if I say the blur x loop nest, there's this command called compute root, which basically means compute it at the root of the hierarchy, which means don't compute it within anybody else's loop nest. So what this code would do is it computes the entire temp buffer. Notice that we've allocated the temp buffer, and then just accesses that temp buffer while iterating in tiles. It's a valid program. Doesn't make that much sense why you would do this, but it's valid. And now what I'm going to do is I'm going to say, hey, this blur x loop, let's go ahead and shove it right here. So that for every tile of output, we first just generate a tile of temp, and then we use the tile of temp. So I'm going to say, hey, blur x, actually I want you to compute it at the xi loop of out, which actually I shoved it in even further. I shoved it into the innermost loop. And so now halide goes, oh, for every innermost loop, every output pixel needs 3 pixels of temp. So I'm going to create 3 pixels of temp, and then we're going to use it. I'm going to create 3 pixels of temp, and we're going to use it. And to get to the code that we actually talked about, I actually want to do blurx.compute at what? I would actually want it to be blurx compute at x. And blurx compute at x would shove that into the x loop. And so it says for every tile, first compute 256 by 34 elements, and then use them. And then throw it out, and compute another set of elements, and then use them. Okay? So the summary of actually getting to the loop nest that I showed you in that assembly code would be those 2 lines of halide schedule. You set up the loop nest for output, and then you figure out where to put the producer inside that loop nest. Okay? So this is actually kind of interesting, right? This is not the most typical of systems. The philosophy here is the programmer is responsible for describing an image processing pipeline. That's the algorithm. But the programmer is also responsible for doing all the conceptual thinking about how to optimize it. And that's the schedule. And there's like kind of 2 cooperating domain-specific languages to do those 2 things. And then the compiler is responsible for basically carrying out its orders. If you're on ARM, generate these intrinsics and this threaded code. If you're on x86, do this. Handle the boundary conditions and the allocations appropriately and stuff like that. So by knowing all of the dependencies, by being functional, basically, there's no pointer chasing or anything like that, the compiler has knowledge that it can move these loop nests around and change all your indexing for you and never change the correctness of the program. So the idea in halide is that if you modify the scheduler, you will never change the output. It's just an optimization. Okay. And then some really early results, which are now basically a decade old, the initial papers show that, we could write less code and actually get higher performance most of the time than hand-tuned assembly. Even if the compiler doesn't generate as good of assembly code as what a good programmer would do by hand, the programmer is able to iterate over the high-level design space more rapidly and try more things. So the global structure was better, even if the code might have been 10, 20, 30% slower than a good programmer. Okay. And so that was the thing. And then Google, some of the folks that did this went to Google. And they did it full-time at Google, even though it stayed open source for a long time. And this became robust enough to be the compiler for the Google image processing pipeline. So that's the history here. So again, I want to emphasize, if we take a step back, like, Halide does not help you write fast code. Well, it doesn't help a naive, non-performance-oriented programmer do anything. Like if you haven't taken 149, how the heck do you even write a schedule? You don't know anything. You don't know any of the concepts. But it helps someone like you all, who kind of know what the space of things you want to try, get through that space of things in a couple hours in an afternoon for more complex functions, right? And it did turn out that there aren't very many 149 programmers. There were, even at Google, there were about 80 programmers that wrote Halide algorithms, and a very small number of programmers that actually wrote the schedules. And I think by a very small number, like 3. Like literally, like when one of them went on paternity leave, like nobody wrote schedules for a while at Halide, right? Now, since about in the last 3 to 4 years, one of the things that these abstractions of the schedule, notice what they do is they give you this very structured, organized design space. The process of optimizing a program is choosing the loop nest and choosing where to put things in that loop nest. And that extremely structured design space has turned out to also be incredibly useful to guide automated search. And so there's been this idea of how the heck do we actually get rid of those 3 programmers at Google for almost most of these computations, right? And we did a little bit of early work on this, and then in 2016 and then 2019, there was a paper that was led by one of the co-creators of Google. I did help with it, but it really was this person, Andrew Adams, who is the big worker on it, that was able to come up with some algorithms that just kind of used game plane techniques like tree search and stuff from an AI class to search the space of schedules and come up with schedules that were pretty darn good, as in like all of you would work really hard to get good, as good as schedules. And I'll show you just some fun results from not this paper. The results I'm about to show you are not as good as this paper, but we'll step back 2 years because this paper didn't have a graph like this. Here was the human study in a systems paper. The x-axis is time. The y-axis is throughput in pixels per second, so higher is better. And these are 3 different image processing applications. Doesn't matter what they are. So we went to 2 of these 3 people at Google that were the best in the world at optimizing schedules. And we said, you've never seen this program before. Here's the Halide algorithm. Please write the schedule for it. And basically the way these folks work is they write the schedule, they obj jump, look at the assembly, and go, yeah, that's not the right assembly. Let me. So they're actually looking at assembly, but never writing assembly. And it's kind of funny is this is what the auto schedule kicked out, like in a millisecond. That's the green line. That's why it doesn't get any better. It's just what the algorithm did. And then this is Andrew and Dylan's performance over minutes of what they were able to get to. So they were just like writing schedule, run, performance profile. Okay, that's not working. Let me try this other thing. So it's like an interactive 149 assignment kind of situation that they were in. And it's pretty impressive. So the auto scheduler won 2 out of 3. I mean, obviously we only gave them an hour. Like if they would have kept going, they would have beaten these things for sure. But the newer auto scheduler is even better than this. It'll schedule a comb layer better than most people. Yeah. Of the program. Like the program that I'm writing got this score on my 149 scoreboard.
Yeah, but I would assume that you would retain your high
Well, this is just what they were trying at the time. So they're exploring the design space. That's why it's going down. Yeah. Andrew is not dumb. He created halide. He's not dumb. But he's trying different things. And so that's him kind of going, I got a good program. Let me see if I can do a little bit better, go in another direction. And like 45 minutes in, he's like, I'm good. I quit. This is not going well. I quit. Yeah.
They don't actually write code, but they look at the object number.
Well, what they do is their methodology. I'm channeling them, and this was a while ago now. Is they were like, oh, okay, I got this performance. I wonder why. I wonder if like it's doing a good job with that inner loop. Let me go look at it.
Program at assembly level.
Not stepping. They're just obs jumping and look. I mean, in their head they're stepping it. Yeah, but in their they just like they have a halide schedule open here in a text editor, and they have a compiler and obs jump open here, and then they're running code and looking at their output. Yeah. These guys are like once you they're just like, oh, I know sometimes like when I do this, LLVM won't loop allocate or unroll this loop. So let me see if LLM's going to unroll this loop for me and stuff like that. Or not LLM, LLVM. Excuse me. Yeah. Cool. Okay. So just to keep it going is sort of this. Like, since so many people are so interested in high performance image processing, there's the question of why are we even compiling to CPUs at all? And so there's a bunch of work by a bunch of different groups. Here's one from Stanford, where they took a language that looked a lot like halide, if you look at it, is a simplified version of halide in some sense, and said, no, we're not going to emit instructions at all. We're going to emit FPGA circuits directly, right? So we're just going to skip the programmable processor and just generate hardware directly from the high level representation. In the last week of class, we'll come back to this topic a little bit more generally, is if you care about performance, why are you taking the baggage of all of these like in some sense, you can think about the ISA, the instructions of a programmable processor. That's the interface between the hardware implementation and the software implementation. But if you're writing in a high-level DSL, why do you need that interface at all? Why don't you directly just have the compiler be aware of the hardware implementation and just generate it directly? And this is the same philosophy behind a lot of these systems that you're using. Like, for example, most of you, TensorFlow or PyTorch or something like that is probably the most common domain-specific language that you're used to working with. Maybe others of you, SQL is probably the most common domain-specific language you're working with. The point being is you can't do a whole lot in those languages compared to the space of programs that you can write in C or Java. But the compiler and the system knows about the semantics of the key operations. And because they know about those semantics, they can do some pretty intelligent things for you. Things that it might be hard for many of us to even do because we're maybe not as experienced or as elite in the domain. And so this is very much where the world is going, especially in an era where there's so many different types of processors. Like imagine you came up with one halide schedule and then you go to an ARM processor, you probably need another one. You want something that knows enough about the type of programs you're writing to try and take some of that off of you. Okay. So those are kind of some of the summary. So we have 12 minutes. Let me just give you another example just really quickly. Just because I want to talk a little bit about the magnitude of optimizations that can occur in high-level languages. So this was a project done as part of a Stanford lab, probably almost 12 years ago. Actually, about the same time halide was being developed, to be honest. And the reason why I like to just use it as an example because there's some pretty big things the compiler does. So this was a high level, like the early goal was to simulate a jet engine, which means you need fluid dynamics and you need finite element analysis and stuff like that. And how many people in here have like a scientific computing background? Every class, there's always a couple that are here because they're like, I'm in SCPD, or not SCPD, ICME or something like that. Anybody? Okay, not present today, but so there's almost always a couple folks in the class that actually do this type of work. And if you've done any kind of physical simulation, you would know that jet engine is going to be represented by a mesh. And we're going to perform operations on the mesh. So the domain that we're working on now is the set of programs where there's not pixels that we're dealing with, but operations on meshes. Okay? And one of the hallmarks of all of DSLs tends to be the system or the compiler knows what your data structure is. So in Halide, it was like everything was a function and the compiler handed the allocation. In PyTorch, everything is a dense tensor and that's it. In some of these, in List or in any of these graph processing DSLs, the only thing you can operate on is a graph. Right? So all of them give you some abstract notion of a graph. And there's 1,000 different ways I can represent a graph in a computer in the same way that there's 1,000 different ways that I can represent an ND tensor. In Halide, we never allocated the whole tensor. We just allocated the chunks that you actually needed. That could be true of graphs as well. So List will never give you a graph structure. It'll only give you a set of functions that allow you to access elements of that structure. So the first thing I want you to look at is this is a program in List which says while not done, while I equals 0 to 1,000, this is time stepping 1,000 times, for every edge in the mesh, do this. So we don't know what the representation of that mesh is at all. We don't know if it's a graph with pointers. We don't know if it's a compressed sparse row. We don't know how the particular computer wants to represent the mesh. All we know is that we have the ability to query for edges. And for every edge, we have the ability to query for the surrounding vertices. And for every vertex, we have the ability to query for the surrounding edges. And then the other thing we can do is not only get the parts of the mesh, we can programmatically say, I'm going to store data on those various parts. So on every edge of the mesh, or every vertex, I might store position, or a temperature, like a heat. Or for every edge, I guess there's nothing stored on edges in this. Everything is stored on vertices here. And so the data is, I could have said v1.temperature, but they've decided to write it this way, which is more familiar for physicists. It's more like a field. So I have a field called temperature, a function temperature that's defined at all points, and I give it the point as a parameter to get the actual temperature. So you can just kind of look at this thing, and so this is just an algorithm that takes position and temperature from the vertices on both sides of an edge, and then computes some computation on those values to compute the flux over that edge and distributes that flux to the various vertices. Details of the computation don't matter. But given an edge, the loop body accesses and modifies fields or data on all of the parts of the relevant mesh. So a List program only can describe operations on reading and writing fields of a mesh. That's the only thing that they can do. Right? But scientists writing these scientific codes, that's how they think about writing their codes. And the mesh representation is chosen by List for you based on whatever computer you're running on. Okay? And so let me give you some examples of that. So what the compiler has to do, or really what you need is the compiler has to identify parallelism. The compiler has to identify data locality. And the compiler has to now reason about what synchronization is required. This is exactly what you've done in all of your programs so far. Except the reason why you've had to do it is because for arbitrary C, I can write code that looks like this. Like, I want you to access a sub index, where index is some function dependent on data that's not known at compile time. So these are the types of things that prevent regular C++ or even Java from doing sophisticated analyses for you. In List, you can't write this code. The only way you can read and write values is by querying them from positions of the mesh. So the List compiler can look at this program and say, okay, this is a parallel loop over all the edges, and every body of the loop is only going to access information on the vertex on either side of the edge. So now all the dependencies are known. And it even knows that we're going to read some values, and then we're going to write some values. And so here's actually a challenge, right? Every edge is going to update values on the vertices, which means what? There's more than one edge connecting every vertex. So now we have multiple writers into this field. So the compiler will need to know that there needs to be some protection or some atomic here. So let me just give you really quickly 2 ways of parallelizing this code on 2 completely different machines. And the first machine is I want you to think about a cluster of computers, don't have a shared address space at all. The only way to communicate is with meshes. Right? So the program is, hey list, here's my mesh topology. Here's my graph. It might be 100 billion nodes. You go figure out how to fit it on the cluster. And here's my program that says I'm going to do work for every edge, and for every edge we touch these vertices. Or I'm going to do work for every face, and for every face we're going to touch these vertices. And list will go, oh, okay, I'm going to take your big old mesh, and I will distribute it across the cluster with like equal number of mesh elements per cluster, and I'm coloring the different regions of the mesh according to what node they went on. Okay? And since List knows that every edge here is going to need maybe a vertex over here, well, that means List can also, if we zoom into a region, we know that these cells might need this information and these cells might need this information. So those are those ghost cells. So that's the data that's copied to other nodes in order for you to read the correct data. And that's the data that has to be written back to exchanged with other nodes every single iteration or step. So this is like you get the message passing from the List compiler if you're running on a cluster. And believe me, that's a mess. Like that's not fun code to write. But imagine we're compiling this List code to a GPU instead. Single address space, many tiny threads. I'm not going to divide this big mesh into like all these tiny little blocks. What I might do, what might be much more natural, would be to take that loop and say, it used to be for all edges in mesh. Well, I should probably do something like there's a CUDA thread per edge, right? But there was this problem, right, where we said that for every edge in the mesh, we're going to write some value to the vertex on one side of the edge and to the other. So we have multiple threads that have to write to the same value. So one solution would be this write needed to be an atomic write. So the compiler could just emit that. But what List did is, atomics can be kind of slow. And this is a graph of the numbers are edges and the letters are vertices. So multiple edges write to the same vertex. So instead of using atomics, which they determined to be too slow, they said, here's what we're going to do on a GPU. We're going to pre-process the dependencies. So again, like the numbers are edges, the letters are vertices. And they said, well, we're going to analyze that, and we're going to actually look at which edges share the same vertex. And we're going to encode that in a graph where edge 1 and edge 5 have a line, an edge between them, if edge 1 and edge 5 in the mesh share a vertex. So you can encode, so 1 and 5 have an edge in this graph because 1 and 5 both write to C there. And notice that there's no edge between 8 and 2, so 8 and 2 do not write to the same values. And then what they do is they take this graph down here and they run a graph coloring. And graph coloring is an algorithm to say I'm going to color, and there's no 2 adjacent nodes that get the same color. And then that for loop over edges is actually going to be broken into, if we have 1, 2, 3, 4 colors, 4 parallel for loops, which means for all edges colored blue, completely in parallel with no locks or no atomics. Then for all edges colored orange, for no locks or no atomics, and so on and so on. And they do this, and they show that the same List program, the folks in mechanical engineering don't have to take 149 at all, and they can run a code on a cluster, or they can run with this many cores, or I'm not showing you here, but they could run a code on the GPU, and without any modifications, they got pretty good performance in both of those cases. So that's the benefits of these high-level abstractions. And that's just a quick summary of some of the ideas behind List. And again, it's sort of typically most of these DSLs are, we're going to handle the data structure. We're going to give you accessors into the data structure that don't actually let you make any assumptions about its format. You write your program in terms of the accessors, and we'll go to town because we know some details about dependencies or the data structures used from that point forward. Okay? And that pattern just repeats. Like if you look at PyTorch, what's the data structure? A tensor, right? And you're not allowed to manage any of that allocation or anything like that. You just ask for tensors, and they say, well, we'll handle it. You just tell us what you're accessing. So there's just a few things I'll just for some riffing is these languages work out well when the structure of the primitives match the natural thinking of the user. So like physicists think in terms of operations on meshes. Image processing people think about operations on pixels. Machine learning people think about operations on tensors. And you really want to get the operations aligned with the thought process. That's really, really important, right? But you also want to think about the process of the performance, right? So a parallel programming system that is really convenient allows you to elegantly express things, but precludes the best known implementations, almost always fails. So the way we like to develop these things is like we write the code down in terms of how would the user want to write things, and then we write the code down again in terms of how do we want it to execute on a real machine. And we start thinking about, is it possible for a compiler to go from point A to point B? What does the compiler need to know? And then we start adding a little bit more to the front end so that the user can just declare that information. That's kind of the process on how to think about it. And then the other thing is that a lot of these systems are incredibly simple. Good systems tend to have only a couple of primitives that are well optimized, and the power comes from composing them. So if you're ever designing one of these things, people are going to come up to you and say, hey, can you just add this? Can you add that? And good architects actually are really curmudgeonly. They say, no, well, like show me why you can't do it in what you have. Because they know that like once you get more than a couple of primitives, like you just start losing control of this thing. Like all the beauty of being able to make a few things fast starts going away. So most of these systems have a very small number of primitives. And if you have a small enough number of primitives, they compose. And so the other thing that really good architects add, so you come up to them and say, if I just had this primitive, my thing would run 10 times faster. And a good architect can think about it and go, but if I added that, it doesn't compose with the 4 other things that I have. Let me go figure out how to do it a little bit differently than what you're suggesting, because we want to be able to compose. And almost every good design that like lasts for a decade or more, the creators kind of come up and go, I had no idea people were going to use it for that. Like I was trying to write this thing for processing meshes, or in the case of graphics, I was trying to write this program for like rendering pictures. And these weirdos at Stanford and UNC started using it for doing protein folding. That means you've actually had a good system, right? Because you have a few small primitives, they composed, and people started using them in ways that you never thought possible, right? And in some sense, like that's one of the beauties that's been so impressive about these LLMs is they were kind of designed to do one thing, and people are starting to figure out very different ways to do it than I'm sure the folks at OpenAI and other places ever imagined. And so something's powerful and you're onto something when someone teaches you a way to use your own system that you're like, I didn't know you could do that in this thing at all. So I'll stop there. But this is more philosophical today than anything else.